Hi folks, in this video we're going to have a look at how we can determine the time constant of a capacitor experimentally. So to do that, we first of all are going to need a battery. In this case, the battery is made up of four 1.5 volt cells. We need a capacitor, and in this case the capacitor has a value of 470 microfarads. We need a resistor. Here we're using a 100 kilo ohm resistor. And we need a multimeter. Now this multimeter will be used to measure the current, and it will be measuring microamps, so that's 10 to the minus 6. We're also going to need a stopwatch, and we need to have a two-way switch, and that two-way switch will allow us to change between charging the capacitor and then discharging the capacitor. So we set up the circuit as shown here in the diagram, so that whenever the two-way switch is put in the up position, then we charge the capacitor, and that will happen very quickly because there's no resistance in that upper part of the circuit. But whenever the two-way switch is in the down position, then the capacitor will start to discharge. That won't happen instantaneously because we do have an extra resistor in there, and we can measure the current as it's discharging using the multimeter. So first we make sure that the two-way switch is in the up position so that the capacitor is fully charged. Then we'll move the switch into the downward position so that the capacitor can begin discharging, and at the same time start the timer. Every 20 seconds we will record the current that we get on the multimeter, and we'll do that for 3 minutes. So now that the 3 minutes is up, you can see that there is still a reading on the ammeter, and therefore that means that the capacitor has not fully discharged. I'm just going to add a voltmeter across the capacitor to show you that there is still a voltage across it. So we're getting a reading of 0.17, and that's now decreasing because of course the capacitor is still discharging because that bottom circuit is still complete. So now we're going to very quickly charge that up again by putting the switch into the upwards position, and you see that that happened almost instantaneously because there was no resistance in that upper part of the circuit. It charged very, very quickly. So with the capacitor fully charged, we can repeat the experiment again to get a second set of results. So with this set of results, what we want to do is to plot a graph. On that graph, we will be plotting the time along the x-axis, and we will be plotting the current on the y-axis. Now the current here is going to be an average value of the current from the two sets of data that we've collected. So you can pause the video here to work out the average current for each set of values that we have. Just remember that the multimeter that we used gave us values for the current to the nearest microamp, and therefore your values for your average should reflect that. So if you get a decimal point when you work out the average, you will need to round that to the nearest microamp. Once you have your values calculated, then you can go ahead and plot your graph of time on the x-axis against the average current on the y-axis. You can then also draw a smooth curve of best fit through those points. So when you plot your graph, it should look something similar to this. What we find is that as time goes on, as the capacitor is discharging, then the current decreases. And in fact, it's an exponential decrease. There is an equation that links the current and the time together. So that equation is I, where I just represents the current. I is equal to I naught, where I naught is the initial current, so the current at the very, very beginning, multiplied by e to the power of minus t, t representing the time, divided by the time constant. Now we're going to use a Greek letter here for this, and it's the Greek letter tau, which represents the time constant. So this is actually what we're trying to figure out. We've collected some data already for the current and the time, and now we want to try and figure out what the time constant itself is. So to help us figure out what this time constant is, we're going to consider the special case where a period of time has elapsed that is equal to the time constant. So what would that do to our equation? Well, what we would have is I is equal to I naught e to the power of minus, and instead of writing t, we're now going to write tau because that's the time constant, divided by the time constant again. Now the reason that we're picking this specific case, hopefully this will make it a bit clear now, is that you can see we have e to the power of minus the time constant divided by the time constant. Now anything divided by itself is equal to 1. So really what we have here is that I is equal to I naught multiplied by e to the power of minus 1. And another way of writing that mathematically would be to say that we have I naught divided by e, because e to the minus 1 is the same as 1 over e to the power of plus 1. So therefore that just means we could have I naught divided by e. Now e is just a number, it's a constant, and we can put that into the equation. So we could say we have I naught divided by the value for e, and I'll just give it to, let's say we've got 4 decimal places here, 2.7183. So what we're really saying here is that at a given time, where that time is equal to the time constant, when that amount of time has passed, that is approximately equal to 0.37 multiplied by I naught, 37% of the original current. So we can use that fact and use the graph that we've plotted to help us find this time constant. And we can do that by working out what is 37% of the initial current. If we work out what that 37% is, then from the graph we can figure out how much time had elapsed before the current reached that level. And that amount of time is equal to the time constant. So from this particular graph then, we would first read off what the value of I naught is, and that will be the y-intercept, the very first point that we plotted. So I naught in this case is 62 microamps. If we want to determine the time constant, then we need to figure out what is 37% of that value. So the current that would give us 37% of that initial value is approximately 23 microamps. So what we're going to do then is find where 23 is on the graph, use a ruler and draw straight across until it meets the curve, and then draw that line straight down. And we can just read off a value for the time, and that time is equal to the time constant. In this case, that'll be approximately 47 seconds. So if we break this experiment down into the 4 key areas, first of all we have the diagram. So you need to be able to draw the diagram with the appropriate circuit symbols, and the circuit should include the ability for the capacitor to be charged and then for the capacitor to be discharged. There's 2 key measurements that we take, and that is time using a stopwatch, and we also measure the current using an ammeter or a multimeter. In order to collect those measurements, first we fully charge the capacitor, then change the position of the switch so that the capacitor is discharging, and we start the timer at the same time as we move that switch. We record the values of the current at regular time intervals. Finally then, to determine the time constant itself, what we would do is plot a graph of the current against the time, and then we would read off the value of the time where that current has fallen to 37% of its initial value, and this is equal to the time constant. So what I would recommend you do now is just pause the video here and make a copy of this page for your notes. I hope that helps.